Welcome guys. So today we are trying to prove this this theorem. So basically this is the binomial coefficient theorem, right? So I think everyone knows about this. So let me just quickly write it. So basically x plus y to the power of n can be written as xn plus yn plus n to the k x n minus k y k from k from 1 to n. Okay, so this is the theorem, but now we just using a commutative semigroup, or basically you can view it's just commutative ring. Okay, so all we need to have is this and the associativity. Okay, so this dot, this circle, I will call it dot. So dot n x just basically x to n. Okay, so dot n y just be the yn, and this dot n minus k, for example, x dot ky is just x to n minus k, y to k. Okay, so this is just the notation, and this is the binomial coefficient. Okay, so we have this. If there's an identity element, then we have this, right? Because now you need to define, you need to have this, right? Right. So basically, you need to have this. Okay. So we are trying to prove these two, right? But basically, if you prove this one, then basically you have this. Okay. So the proof, we basically first is established when the result has identity. So we can check that n equals to 0, n equals to 1 is correct. When it's 0, then this is n, right? This is n, right? So 0, 0, then we have this, right? We just check this, right? But this is all 0. This is identity. Okay, and for this one, n equals to 1, this is 1, so it's just x plus y. And we have 1, 0, 1, right? Take this is this, I think this is incorrect. This is 1, 0. So this is x. This is just y, right? Because this is identity, and this is 1. Okay. So n equals to 2. You just, for example, like we just doing using the we just expand it. Then we have this. Then this becomes this, right? This is these two terms, and this term can be written as this term, and change into this. So basis for induction. Okay, so finally there is an induction step. We assume that when n larger than 2, we have this. Okay, so induction step just add x plus y term, right? Become this, right? So this become this. Then we just separate it as x and y term. Okay, so x term become this. Let me just maybe x term become this. Just we just, so this term, this first term, and the second term just add 1 at x here, and the x here, and this is y term. So we can combine the first. So we already have this, and we already have this, right? So finally we need to combine these 4 terms. This term. Okay. So for this term, right, we can just, so this x dot and y term can be absorbed by n term, right? So we add 1 when k equals to n term. So we can absorb this term into this, and this term into this. Okay. So we have these 2 terms. Okay. Okay, so this term is remaining, this term become this term become this, and this is remaining. So combine these 2 terms. We use the Pascal rules. So Pascal rules I already proved in my previous video, but basically it's this. And if you don't know that, you can go back to see my previous video. There's a detailed proof. Okay, so we use Pascal rules. So we combine these 2, and you get this. Okay. So finally, this is just the original expressions for n plus 1. So we finish the induction step. Okay, so that's all the proof, but basically there's nothing there's nothing special. We're just using the standard multiplication and standard operation. Okay, that's it, and I will see you guys in other videos. Be sure to subscribe to my channel. Thanks.